In this video, we will talk about Bernoulli's equation. It is an equation in fluid mechanics that relates pressure, speed, and height of an ideal fluid flow. We will see that it is a consequence and therefore a statement of conservation of energy that relates work done, kinetic energy, and potential energy. Finally, we will solve a few problems based on these concepts. Let's look at the idea and concepts behind Bernoulli's equation. Assume that you have a following system. So you have a pipe and you have fluid flow within that pipe. Let's look at 2 points along the pipe, point 1 and point 2 there. At point 1, let's say the fluid is moving with a speed of v1 meter per second. The pressure at site 1 is P1 Pascal, and point 1 is situated at a height of h1 meters above the ground. Likewise, at point 2, the fluid or the liquid is moving with speed v2 meter per second. The pressure at that site is P2 Pascal, and point 2 is situated at a height h2 meters above the ground. The volume of fluid that enters from the left must be the same as the volume of fluid that is leaving the right side of the tube, because the fluid is incompressible and therefore has a constant density. As this portion of fluid moves through the pipe to point 2, its kinetic energy changes because now the velocity or the speed changes, and its gravitational potential energy will also change because the height from the ground now also changes from h1 to h2. These changes on mechanical energies are due to work done on this volume of fluid as it enters and leaves the pipe. Thus, Bernoulli's equation relates all these variables according to principle of conservation of mechanical energy, which can be written in the following form. Now, as you can see, the term half a rho v1 squared and half a rho v2 squared, with a rho being the density of that fluid, are kinetic energies per unit volume of fluid. Likewise, the terms rho gh1 and rho gh2 correspond to gravitational potential energy per unit volume of fluid. Thus, the term P1 minus P2 can be viewed as the work per unit volume of fluid. Thus, by rewriting the Bernoulli's equation in a following manner, we can see that the work per unit volume of fluid is equal to the sum of the changes in kinetic and potential energies per unit volume. So one can clearly see the conservation of mechanical energy in action here. Note that Bernoulli's equation works for ideal fluid. That means the fluid must have a zero viscosity, and the reason is that if not, the thermal energy need to be considered from the action of viscous forces. Let's look at 2 special cases of Bernoulli's equation. The diagram here shows fluids at rest. Let's say you have a surface of lake or a pond where obviously the velocity of fluid on the surface is 0, and at the bottom is 0 as well. So you have a fluid at static equilibrium. Let's compare 2 points, the point at the surface of the lake and the point at the bottom of the lake, and write down the Bernoulli's equation relating quantities at these 2 points. So Bernoulli's equation says the pressure at the surface, P1, plus, since the velocity is 0 at the surface, there is no kinetic energy term there, but point 1 is at a elevation h from the ground or from the bottom, so we have the potential energy term, let's call it rho gh, and that must be the same, the pressure at the bottom, P2, plus rho g, where the elevation now is 0. So by Rearranging the terms, we see that P2 minus P1 gives a rho GH, a result that we have seen before in one of our previous videos. The right-hand side of this equation is known as the gauge pressure. So in other words, what this equation is saying is the pressure due to this much of liquid column is quite simply rho GH. Special case 2 is when the 2 points are at equal height or equal elevation. So let's say you have 2 sheets, could be 2 sheets of paper, sheet 1 and sheet 2. So the pressure outside the sheets is, let's say, P naught, and the speed of air, let's say, speed of any fluid that is moving outside the 2 sheets is V naught. Within the 2 sheets, the pressure is Pi and the speed of fluid is Vi. So let's write down Bernoulli's equation for the system. So Pi, the pressure inside or pressure between the sheets, plus half the density of fluid times the speed inside squared plus the density of fluid gravitational acceleration times, let's say, the elevation is h naught. And now for the outside, the pressure is PO or P naught. The kinetic energy term is half rho V naught squared, and the elevation is still the same. So you see that the potential energy terms will get cancelled, and you can write the following, rearranging the terms, and you get the following results. What this equation is saying is that the region with the higher pressure would have a lower speed, and vice versa. As you can obviously see from here, P naught is greater than Pi, then Vi must be greater than V naught. Let's look at problem 1. A cylindrical tank with large diameter is filled with water to a depth of 0.4 meters. A hole with cross-sectional area 6 cm squared, that's right there, in the bottom of the tank causes water to drain out. Calculate the water flow rate out of this hole in cubic meters per second. In order to calculate the volume flow rate, you need to know the speed with which the water is flowing out of the tank. Now the speed on the surface is of course 0 meter per second, and the pressure at site 1 on the surface and the pressure outside when the water rushes out, P2, must be the same. So by applying the Bernoulli's equation, we get P1 plus half rho 0 squared plus rho g 0.4, so this is for the surface, equals P2 plus half rho v squared, v is what we want to determine, plus a rho g, and the elevation of the bottom of the tank can be taken to be 0. Now note that since pressure P1 and P2 must be the same, they are atmospheric pressures, so that goes away. This is 0, this is 0. The density will cancel, and we can immediately solve for V. And solving for V, you will get 2 times gravity times 0.4 square root, which is 2.8 meter per second. The equation of continuity would tell us that the volume flow rate is quite simply the cross-sectional area times the speed. So if you take the cross-sectional area here and multiply with the speed there, you will get the volume flow rate. Now we do know what the cross-sectional area is. It is 6 cm squared, so we need to convert that to meters squared and then multiply that with the speed that we have just calculated, and you will end up with 1.68 times 10 to the power minus 3 cubic meter per second. And that solves the problem. Problem 2. Stream of water flowing out through a hole at a depth of 8 cm, that is the hole, in a tank containing water to height of 40 cm. Find the distance x the stream strikes the floor. So let's write down Bernoulli's equation relating point 1 and point 2. So point 1 is open to atmosphere, so the pressure there is atmospheric pressure. Let's write it as P naught, plus this is the surface of the tank. So the water there is still, it's at rest, it's not moving. So speed there is 0. Point 1 is at elevation of 40 centimeters. So the third term will be density, gravity, converted into meters, 0.4 meter. And that equals, now the terms outside here. So the pressure is still the atmospheric pressure, P naught, because it's outside the tank. Now the kinetic energy term is half rho. Speed is what we want to determine, so we don't know that. Now the elevation of that hole measured from the ground is that distance right there. So that is 40 minus 8, 32 centimeters, or 0.32 meter. So that will cancel. This is 0. Now all the terms have density in them, so that will go away. And the equation that you have is half v squared equals g 0.4 minus g 0.32, and you can solve for v, and v will turn out to be 1.253 meter per second. Having determined this speed, now we can proceed to determine the distance x the stream strikes the floor using kinematics. Note that the stream of water will travel the horizontal distance x in the same time as it would travel the vertical distance y. So let's determine the time the water stream takes to travel the vertical distance y. Now we know what y is. Y is quite simply 40 minus 8, which is 32 centimeters. So y equals half at squared. Since initially the velocity is purely in x direction, there is no y component to its velocity. So that kinematic equation, the second term of that kinematic equation is 0. Now since y is 0.32 meters, we have converted cm to meter. Half gravity is the acceleration, so it's 9.81 t squared, and you can get the t. And when you do that, your t is 0.255 seconds. And now using the fact that the initial horizontal component of the velocity does not change because gravity acts vertically downward, so gravity has no effect on this initial value of v, we can determine x. X is quite simply vt. So v is 1.253 and t is 0.255 seconds, which will give you 0.32 meter or 32 centimeters for x. And that solves the problem. Thank you for watching.